Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its advanced analytics solutions for oil products distribution. The distribution chain of petroleum products. The oil and gas supply chain is made up of 4 links: upstream, midstream, downstream and retail. The links are connected by multimodal transport networks. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides and plastics. The table, elaborated by IBM, shows a resume of the optimization solutions for oil and gas enterprises. The distribution chain of petroleum products begins in refineries, and ends at the sites of consumption of different types of products. Optimization solutions in the transport and distribution chain of petroleum products can be classified by their hierarchy: strategic, tactics, and operating. Several of these applications will be discussed below. Oil products transport, trading, and blending optimization corresponds to a dynamic model that optimizes oil products distribution between refineries and ports and terminals, the oil products mix in the terminals, the mixture of oil products for export in accordance with quality standards, and establish supply contracts, import of oil products according to offers in the spot global oil products market, and import and export of oil products according to offers in the oil products derivatives financial instruments. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. Oil lubricant blend a nonlinear optimization process. The physical and chemical properties of oil products change when they are blended. The linear or nonlinear relationship between this change and the properties of each blending component is expressed as an additive effect between the components. A certain physical and chemical property equal to the superposition of each component according to its composition ratio is called linear harmony, otherwise, it is called nonlinear harmony. The chemical composition of oil products and additives is very complex, and their physical and chemical properties generally do not have an additive effect, so the blending of lubricating oil is mostly nonlinear. In addition, the performance indexes of lubricating oil mainly include viscosity, freezing point, acid value, flash point, oxidation stability, residual carbon, and so on. Therefore, the optimization of the design of a lubricating oil blending scheme mainly includes 2 aspects: to select the base oils reasonably to meet the performance index requirements of the blended product, and to establish the blending mathematical model, and determine the blending scheme of each base oil, on the premise of meeting the product performance indexes. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. Oil transport systems optimization corresponds to a general model, common to all types of oil products, raw, refined, natural gas and biomass, which represents the process for a specific system, including particular equations when this is required. It considers 2 types of transport modes: pipes and multimodal vehicle, like vessels, barges, train tanks, and/or trucks tanks. The integrated transport system can be conceptualized as the junction of pipe and vehicle routes, which interconnect multiple terminals, which are the places where are connected the different installations. Each transport media is modeled independently. System connectivity is done through the terminal, a node, that corresponds to a point in the space in which at least 2 installations are interconnected, such as oil fields, plantations, oil refineries, biorefineries, port, consumer centers, and thermal plants. The table presents a summary of the oil transport mathematical models developed by HI. Pipelines planning and scheduling. HI supports the planning and scheduling of oil products transportation through pipelines using 3 coordinated hierarchical models. Tactical planning determines the optimal volumes to be transferred in during the planning period, without considering the sequence of products in the pipelines. Batch scheduling determines the volumes and sequence of tenders to be transferred in during the planning period, considering the volumetric planning established at the previous level. And real-time optimization determines transfer speeds, discharge pressures, and pumping patterns, serial or parallel, at pumping stations, to meet batch scheduling established at the previous level. The optimization goal is to minimize operating costs throughout the entire planning and scheduling process. The real-time models includes nonlinear modeling that determine the amount of energy consumed based on the flow of products in the system. In aggregated models, when multiple types of products can be transported in the pipeline, the total transport time must be divided into the time used to transport each type of product at different transfer rates. To represent the flow of energy through the transport system, the following constraints should be considered. Energy conservation in the ducts and nodes of the system. Minimum pressure limits, or compression, at the outlet of the ducts, and pressure, or compression, minimum input to the ducts, depending on the type of connection between the operational area, node, and the duct. In the real-time model, a detailed hydraulic system is available in the pump operation model, for each type of pump in the pumping system, and each link in the pipeline, for each type of product, or crude. This ensures the feasibility of the results. The real-time model can handle differentiated electricity costs by time of day, or by load block, using this way to take advantage of low rates, or low marginal costs, in periods of electricity low load. Natural gas supply chain optimization. Similarly, like oil, natural gas supply chain may be modeled as an optimization mathematical model to simulate the transportation and storage of natural gas. The diagram presents the natural gas supply chain. The main features are: natural gas is produced in gas wells, or as an associated product in oil and gas wells. The marketing of gas implies that it can be transported massively by means of gas pipelines, or in ships. For this it is required to turn it into liquid, in liquefaction plants, and later converted back into gas, in regasification plants. This usually happens at terminals in port. Transportation through pipelines requires gas compression stations, y. Finally, the gas is delivered to a market, usually segmented, in industrial, vehicular, residential and commercial, and thermoelectric plants. As integrated products, electricity and gas must be modeled together. As a basic energy, the natural gas is a raw material of electricity, and in turn, as useful energy, it is competition of electricity. The optimization model includes the following types of nodes. Production fields. Consumption center, natural gas demand nodes discriminated by demand sector, among which are industrial, vehicular, electricity generation, commercial, and residential, and ports and terminals that can receive and/or send LNG. It is associated with liquefaction and/or regasification plants. Similarly, like oil and LNG, liquefied petroleum gas, LPG, distribution chain may be modeled as an optimization mathematical model. Liquefied petroleum gas distribution chain optimization. A mathematical models for distribution planning and propane gas containers gathering. It is aimed at supporting the weekly and daily programming and operational rescheduling of trucks dispatch. The modeling hypotheses are as follows. Fleet of vehicles consisting of multiple type of trucks and multiple type of LPG trailers. Trucks can be moved with or without trailers. A truck can tow some type of LPG trailer. LPG trailers can be dispatched with or without charge. Vehicles move between nodes, or terminals. In the nodes there may be demands that must be met, or purchases that enter LPG into the system, and LPG storage tanks may exist in the nodes. Vessel scheduling optimization supports the programming of collection and/or distribution operations of products via maritime ways, in tankers and barges. It considers restrictions for delivery and load time windows, distribution of capacities on ship, loading and unloading capacity at the docks, draft capacity of the spring, speed of movement of ships, tanker weight to draft ratio, and synchronization of filling, or emptying, of storage tanks. 7th. Planning and scheduling of bulk port terminals. The objective is to minimize the terminal operating cost, considering the system environment, which may include the fuel cost of ships. Managing bulk ports and ships becomes part of the industrial process, since it defines the supply of raw materials and the distribution of finished products that are related to industrial operations. Depending on the specific case, it must be coordinated. The arrivals with consumption in industrial plants, the departures with production in industrial plants, and the storages level with the output of material. The optimization may affect the industrial process's speed and the ship's speed. When it is necessary to make decisions about the displacement of the vessel, it is of fundamental importance the correct modeling of the consumption of energy, which has a nonlinear behavior, with respect to the engine speed of the vessel. This constraint can be included in the mathematical model, as well as the modeling of tidal movements when entering or leaving ports. One example is the distribution of petroleum products, along the Peruvian coast, which originates from the Talara refinery, in the far north of the country. The products must be distributed in 8 ports with terminals to store the products, and then distribute them to the interior of the country. Oil product distribution optimization supports the scheduling of gasoline distribution operations, between terminal products and from product terminals to gas stations. It is applicable to several oil products like gasolines, LNG, LPG and others. The oil products distribution logistic chain has 2 major parts, or sub-chains: marketing and distribution itself. These chains are composed of the following links: source, integrated buy, refining, and import; mass storage, integrated buy, mass storage terminal, TAR; transport, integrated buy, ducts auto tank, train tank, and tanker; dealer storage, integrated buy, distributor storage terminal, TAD; and retail, integrated buy, service stations, industrial, and end users. The image shows the Mexican logistics network for the distribution of petroleum products, which reflects all the elements described above. Distribution of gasoline and other oil and gas products between terminals, service stations and industrial clients. A mathematical model of distribution of petroleum products or similar should consider the following constraints: delivery time windows, tank trolley capacity, distribution of tank trolley capacities in multiple compartments, product availability at service stations, product availability at terminals, load capacity of cargo islands, fillers, work shift, and driver assignment. The result is the scheduling of activities by filling pump, filler, tank car, end user and drivers. Considering restrictions for delivery time window, tank car capacity, distribution of capacities in tank cars, load capacity of cargo islands, and work shifts. The entities of the model are terminals, tanks in the terminals, loading points, service stations, trucks, and drivers. For a large distributor, the mathematical model may include transport between terminals, and the connection of terminals with other facilities, such as ports and refineries. Modeling can include all types of transfer between TAR and TAD terminals. A terminal is composed of multiple docks, each of which has one or more truck handling servers. These can be dispatch, or reception, or mixed. Trucks can load 1, 2 or 3 types of fuel, depending on the number of compartments. In urban regions, vehicles can provide 1 EDS, or multiple EDS, in a cycle. In rural regions, vehicles must provide multiple EDS, in one cycle, which can last more than a day. The diagram shows a TAD terminal, which has 5 trucks. Each truck has different costs, fixed per use, and variable per kilometer. The TAD must attend 4 orders for gasoline delivery. The result is the scheduling of the fillers in the terminals, directly associated with the truck dispatches, and the assignment of drivers, which can cover several shifts. The model produces the following results: schedule by island, service schedule by tank, assignment drivers, and indicators use resources. And the following features: restrictions on driver shifts, flow rates per installation, rescheduling assignments, and synchronization with systems. The fuel inventory projection is essential to control the feasibility of truck loading scheduling. The moments when a tank is empty determine that it is not possible to load trucks to transport a specific fuel. The moment of tank supply releases this restriction. The inventory management in the different terminals, TAR and TAD, is the most complicated to model in this type of problems. High guarantees the correct modeling of this aspect, fundamental to guarantee the feasibility of the plan. Case: Mobil's product distribution optimization. This case is based on the paper Real-time, wide area dispatch of mobile tank trucks. In 1987, Mobil reported the benefits of the computer-assisted dispatch (CAD) system. CAD is a scientific computer system, based on optimization models, that supports dispatchers to schedule the supply of the entire gasoline distribution network. CAD began operating in 1985, reporting savings of $3 million per year the operation in the U.S., which generated an income of $6 billion. Among other benefits, CAD reports centralization of dispatch operations, better control of the operation thanks to the integrated system, better customer service, compliance with regulations, for example, legal weight limits, and more ability to assess fleet productivity. Oil products trading. The market for petroleum products is fully globalized. An example is the Japanese market, which to meet their needs, must acquire products in multiple markets, and coordinate all relevant actions, to have the products in their own market. The phase prior to the distribution of petroleum products to final customers, is the negotiation that distributors must carry out to acquire the products. The optimization of this process involves the coordination of three types of interrelated activities. Sourcing optimization. Its purpose is to support all the processes of purchase of liquid fuels, taking as reference the offers presented by the suppliers to obtain these inputs necessary for the productive and commercial systems of the company. In this case, at least the following purchase alternatives may be considered: bilateral short, medium and long-term contracts, negotiations in the spot market, and special offers with the suppliers. The result of mathematical modeling is the determination for each bidder, how much and when to buy, and under what business modality. Combustible distribution. Its purpose is to make the assignments of the products purchased to the different markets that must be served. This considers purchases made, the demand in the different markets, the operational characteristics of the terminals, and freight and availability of means of transport, own and third parties. The result of mathematical modeling is the determination of the volumes that will be transported between the product terminals and the specific customers in each market for each product. Pricing optimization. Its purpose is to generate the necessary information to determine the prices that must be established in the markets in such a way as to maximize the utility of the company while minimizing the operating costs of the wholesale market of petroleum fuels. The result of mathematical modeling is the establishment of a lower limit for prices for each specific customer in each market. This may be obtained looking the dual variables of the combustible distribution model. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.